Hello and welcome to Assembly Language Sound Part 6. This was supposed to be a short series. I don't know how we're all the way up to Part 6 yet, and this isn't even going to be the last part. It's just taken me a lot longer to do things, and I don't know why, but I guess that's always... Anyway, today we're going to talk about how everything can run in the background, and we are going to attempt to run a basic program in the foreground while music is playing in the background. And my friends, there will be a lot of bugs, and I found them to be interesting enough that I just left it all in for your amusement and information. I apologize in advance. As with the previous two parts, I do want to acknowledge Paul Fiscarelli and Simon Jonason for this ingenious four-voice music player that Simon let me take a look at. These videos would not have been possible without me being able to refer to and learn from, and ultimately stealing from, the code of this awesome player. So thanks, Paul and Simon. Here's the older version of all of this code from previous parts and how it treated durations. So this is not the horizontal sync interrupt handler. This is just the routine called by BASIC to play a single note. What it would do is do all this initialization. It would then enable the interrupts, and then the horizontal sync interrupt would handle talking to the DAC. But in the foreground, we would sit here and wait. And when the wait was complete, we would disable the interrupt and return back to BASIC. The wait routine used the duration value that BASIC had given it to just loop, 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 loop. So what was happening there is in the background, the interrupt handler was taking care of the DAC, and in the foreground, we were just waiting until that duration was expired, and then we would return back to BASIC. I'm switching things up because I would like to be able to do something constructive in the foreground, and I'm kind of thinking ahead toward that. I'm not getting there quite yet, because now what's happening in the foreground is I just wait forever. But I allow the interrupt handler to advance through the song itself, rather than BASIC having to send us note by note and have each one play immediately, and thus BASIC was really the sequencer, the thing that would advance from note to note. Now I'm handling all of that in assembly language, and it's not happening in the foreground because the foreground is just stupidly waiting. Hopefully temporarily. Again, I would like to do something constructive here, like, I don't know, run some more basic code. So instead, I'm having the interrupt handler deal with things like durations and deal with things like advancing to the next note. So most of the time, we're just going to be sitting here grabbing values, adding them together, sending it out to the DAC, and getting out of there. But some of the time, I need to be checking my duration count and seeing if it's time to move on to the next note. So this advances a counter that will tell us if it's time to look at the duration or not yet. This is like a duration multiplier. If we had to deal with the duration every single time through this interrupt handler, we would be using up way too much time. So this is kind of a shortcut to say only every FF times through, every 255 times through, should we pay attention to the duration. And all the other times, we're going to be using self-modifying code to change an 8-bit value that goes from FF down to 0. And when it hits 0, then we'll go and do some duration stuff. So specifically, we load A with that self-modifying code to tell us the current value. If it's 0, then we skip all this stuff and do some duration nonsense. Otherwise, we decrement that value and we store it back. So check duration is sort of our gateway into the other stuff. Rather than sending a byte out to the DAC, we do this. So this checks another counter. This is the thing that BASIC has control over. So BASIC will decide how big this number is. We will decrement it, and if it goes down to 0, then we know we need to advance to the next chord in the song. So this is our sequencer. But if not, we get out of there. We reinitialize the multiplier, which is this, back up to FF, store it, and then we get out of here. We go to sound out done. Okay, but what happens when the duration counter, the real duration counter, gets down to 0? Well, then we go to the next chord in the song. And this is nothing more than some bookkeeping, advancing of pointers, and then writing of the new values. We load U with the next pointer into the song, and this is self-modifying code that will advance through the song chord by chord. And then we go into the struct that U is pointing to. We grab the first voice, stick it into D, and then use self-modifying code to put that as the frequency value for the first voice. And that, of course, is right here. So that's how that gets updated as we go through the song. We do the same thing for voice 2, stick that back into its freq value 2, and although the version of the code I'm showing you is the one where we only have 2 voices at a time, we would do this for all 4 voices as well once everything is put together. We reset the wavetables back to the beginning, because we're starting new notes. And so this then updates those self-modified code, wave offset 1 and wave offset 2 back to 0. We reset the real duration count. So this is self-modifying code that BASIC controls. BASIC is the thing that comes up with the value that we use to restore the duration each time it has counted all the way down. We store that here in duration left, and duration left is the value that we check when it's time to check duration. That's the thing that we keep decrementing down to 0. Then we advance U to the next chord info. So we go by the size of the chord info struct and add that to U. And we check our boundary condition. If we hit the end of the song, we're just going to cycle back and go back to the beginning of the song. So the song plays on infinite loop. And in either case, this will write the play pointer into self-modified code so we know where to grab the next chord from. So load play pointer is just that value up here that we had grabbed to figure out where you should point in order to read the next couple voices, voice 1 and voice 2. All right, that's kind of a lot. It probably seemed more complicated than it really is. It's really just a lot of bookkeeping. But that's the whole thing. Unfortunately, this means that our horizontal sync interrupt has a lot more code in it. Fortunately, we execute the vast majority of that code the vast minority of the time. These helpful instructions up here help us avoid all of that code except 1/256th of the time. And even then, each point in here, we kind of bail out unless it's really time to do the next thing. We check the duration and decrement, and that might be all we ever do. Or if the duration ran out, then we have to go to the next chord, and we have to advance the next chord and rewrite everything, and that might be the only thing we do, unless we hit the end of the song, in which case we have to cycle back to the beginning. So only the things that we need to do we do, and then we bail out as fast as we can. So the long and short of it is, between chords, there might be a tiny gap. There might be a little bit of a pause, and hopefully it will not be noticeable. And so with that all in place, I am ready to cut the ribbon. Boom! So now, play song, as called from BASIC, will return immediately. It has initialized all of the self-modifying code from the interrupt handler. It has enabled the interrupt handler, and it comes back. So BASIC regains control at that point while the music plays. I have also integrated back voice 3 and voice 4, which we sum together, along with all of the other code you just saw, so everything runs in the background. And as my experiment, I'm taking a type-in program from a magazine from long ago that draws and paints a picture of a house and animates a car running in the street in front of it over and over again. And all of that code is as it was. But at the top, I added a GoSub 2000, which runs the new code that interfaces with assembly. It uses the sine wave to play this beautiful piece of music. Let's run it on some real hardware, my real Coco 2. you have to understand that before I recorded this on real hardware, I did try this out in MAME, and it was fine. I have not heard this before. It was fine in MAME. I don't know what's going on. And if I'm running into an issue where the emulator is different from the real hardware, and thus I can't debug it using the emulator debugger, I'm not sure what I'm going to do. But what I normally would do in a situation like this is just reduce it down to the simplest possible case that is sure to succeed, and then slowly add things back until it fails, and then I'll kind of have narrowed down where everything went wrong. So what I'm going to do is just play a single note at a time, no chords, and I am going to stop trying to do basic in the foreground. So I'm going to add back that infinite loop in the assembly language routine so that the foreground is doing nothing but spinning, just like it was in the previous parts. And then we'll slowly start adding stuff back and see what it takes to get it to sound bad like that. What the? Can't fucking bull. Work fine in MAME. This is fucking driving me nuts. Can't stand this anymore. Well, this was a bit of a frustrating one. You never want the behavior of the emulator to be that different from the behavior of real hardware. So I was trying to think, am I doing anything that unusual that other people wouldn't have run into this? What are the typical things that an emulator does differently from the real hardware? And I guess one of the most obvious things is uninitialized memory is going to look different. In something like MAME or XOR, uninitialized memory tends to be pretty clean, like a bunch of zeros or a bunch of Fs or a striped version of that. And on real hardware, it could really just be anything. It could be a whole bunch of junk. So I was thinking, where could that uninitialized memory exist that would cause all this weird stuff? And I focused a lot on the waveform, but the waveform is fine. And I did wonder about the direct page register, like was I not properly initializing it? And I do have it initialized every single time the horizontal sync interrupt handler is called. It's not like it used to be where I would initialize it at the very beginning and then assume it would stay that way because maybe it might get changed by BASIC or something. So I was doing this already, but I still used a debugger to double check, and it worked fine in MAME. This is not the sort of thing that would be different between MAME and real hardware. And as I listened to the issue over and over again, it did sound to me like some notes were fine and some notes were like there were extra notes being played in a chord that shouldn't have had more than one or two notes anyway. So that's when I took a look at my add chord subroutine that BASIC calls, and that loop, which fills up the chord info struct with whatever BASIC gave it, and it occurred to me, oh, I'm filling in the voices that BASIC gives me, and I'm not filling in any voice that BASIC doesn't give me. I'm just leaving them as they are. Each chord info has 16 bits for each voice, and if I'm not filling them in, goodness knows what they'll be. So the solution was obvious. Just be sure to initialize all the voices to 0 before we start filling them in with whatever BASIC gave us. And in fact, this made a lot of sense because in MAME, if the voices are already initialized to 0 because it's uninitialized memory, then we would just be hearing nothing for the voices that BASIC didn't care about. But on real hardware, we would be hearing garbage. So this fixes it. Let's take a listen. Why is add chord so slow? Add chord is supposed to be instantaneous. All these notes are supposed to be added in a split second. We're not even playing anything. We're not even playing anything right now. What on earth is this thing doing? Oh, geez. Well, at least that sounds clear. At least that bug is fixed. I went back into add chord and I was thinking, what on earth could make this be taking so long? Is there like some loop that's going out of control? and I looked at the code that I just modified, and then I saw, now that I have added this code, I have trashed my B register, which I was relying upon. B is the length of the string that BASIC gave us that contains the chord, and that was governing how many times we would iterate through the loop as we would read each note from that string. So if B is garbage, we're probably iterating through that loop goodness knows how many times each time a chord is added. This is a common thing for me. I'll make a very quick change, and all the invariants that I was carefully adhering to before I kind of forget about, like, the values of registers and stuff. No matter. That's just a simple moving here. So now we're fine. Now I'm zeroing out the memory before I write to it. My X is cool. And so I can load up my B, my X, and my U, and we are good to go. What? I didn't change any of the basic code. That looks fine to me. Oh, geez. Maybe there's something around there that got bad? No. That all seems fine. Maybe if I just get rid of line 20, which does the load and... God, what the hell? The 10? There's nothing wrong with 10. Come on. Oh, jeez. What the heck? Just start over. What are you talking about? Yeah, okay. Just turning it off. Turning it back on again. We'll start over with drive wire. From the beginning. Execute drive wire. Now run it. Everything is clean. God. What the? So here's the code again. I have figured it out. Have you figured it out? I'll give you a hint. It is related to all of my mad, hasty, rushed changes. Remember, I had grabbed this block from up here so that the trashing of D, and therefore A and B, would happen before I reinitialized B. But what about this? This initializes U, which I need to be initialized before I start writing anything into it. You know what U is at this point? Yes, neither do I. I guess it was probably maybe some memory that BASIC was relying on, because BASIC was going crazy. So we need this to be here. Now U is initialized before this, and B is initialized after this. Okay, now it's certainly going to work. Okay, so we're playing notes and they're fully initialized. Add chord is good and fast. We're not corrupting any memory that BASIC is relying upon. We should be ready to go back to trying to paint that house with some music in the background. Thank goodness, it sounds pretty good. And there's something thrilling about seeing the command paint running in the foreground while something's happening in the background, while song is being played. This is something back in the day I wouldn't have thought was possible. But of course there is a price to be paid. Things are slowed down. So actually let's compare the speed of this with the speed of that original program running without any of the music in the background and without those horizontal sync interrupts. Okay, yeah, it is a lot slower when you have the background music playing, but it still works. We actually now have chords and they're playing in the background while a basic program is running, and that alone I think is pretty darn cool. In the next episode, we're going to do a few odds and ends, a few little polishes and finishes, one of which I alluded to in the previous part. Perhaps if you're following along, you remember that I left a little bit of a loose end there that we need to fill in. And I think that might be it. I think we might be ready to say done. I think. Until then, thanks for watching.